Hello again, everybody. Let's move on to the second talk of the day. We have Jaco Ruit, who's going to talk to us about a double infinity categorical approach to formal infinity category theory. Please, whenever you're ready.
Yes, thank you very much for giving the opportunity to give a talk here, and yeah, especially also thanks for organizing this wonderful workshop. Yeah, so today I want to present something about my PhD research, which is about an infinity categorical extension of the notion of pro-arrow equipments, where we view pro-arrow equipments as certain double categories with extra properties, which was sort of this perspective was introduced by Dominic Verity, I believe. So I could imagine not everybody in the audience is super comfortable working with infinity categories, but I aim to stay away from any technicalities surrounding this. So I believe if you have a firm background in category theory, you will have no problem following this talk and just sort of believe that everything from category theory extends to infinity category theory. And yeah, in particular, this talk will sort of attest to this principle. So we will see that the definition of pro-arrow equipments can be sort of redone in this higher categorical setting. So before giving a plan for this talk, I want to talk about some motivations for this project. So yeah, it starts with the observation that there are many flavors or variants of infinity categories. So one of them is enriched infinity categories. So in this context, you have V, a monoidal infinity category, and then you can make sense of what V enriched infinity categories are. So there are some models for these type of objects due to David Gepner, Runa Haugseng, Vladimir Hinic has written something about this. Jacob Lurie in higher algebra defined a model for enriched infinity categories, and there are definitely some more people to put on this list. So there's already some technicality here that doesn't appear, I think, in ordinary category theory, that here you really have to give a model for enriched infinity categories. And these models, especially for enriched infinity categories, tend to be quite complicated. But in any case, there are definitely some useful examples of enriched infinity categories. So maybe if you like homological algebra, you have seen these DG categories, and you can view DG categories as infinity categories which are enriched in a derived infinity category of abelian groups, if you know what these terms mean. So like originally, DG categories are defined as just being ordinary categories enriched over chain complexes. So really what this example says is that there are some rectification result which associates a category enriched in a derived infinity category of abelian groups to a DG category, and this sets up an equivalence between their homotopy theories. So this would be a more precise statement of example one. And then there's this other definition which is super useful because you can define infinity n categories as categories enriched in infinity n-1 categories. So this will give you some inductive definition of what infinity n categories should be. So hopefully one of these examples speaks to you. Then we have this other flavor which goes by the name of internal infinity categories. So in this infinity categorical context, the role of sets is now played by the infinity tuples of infinity groupoids. Or maybe you've seen them appear as Can complexes or SCW complexes, but I will call them spaces throughout this talk. So I will denote this infinity tuples of infinity groupoids by this curly S that appears on the screen. Well, for instance, why is this true? So an infinity category has a space of objects and spaces of maps between objects. And usually if you deal with ordinary categories, these will just be sets. But in this higher context, they are really spaces. And now the idea of internal infinity category theory is to replace this tuples of spaces by a different infinity tuples E. And then you obtain a notion of infinity categories which are now internal to E. So now this internal category doesn't have, like the object of object, so to say, would be an object of E, where it used to be a space originally. So you can make this very precise, and in fact, E can be any finitely complete infinity category to run this definition of internal infinity categories. And well, this has been extensively studied by now, so there are definitely some names to mention here. So we have the work of Louis Martini and Sebastian Bohr, Nima Rasek, who is also in the audience here and gave an excellent talk just now. And then we have Jay Shah. So I should mention here, Jay Shah works in a slightly different generality. So he works internal to pre-sheaf toposes rather than internal to general infinity toposes. And yeah, and there are, again, more names to put on this list. So also internal infinity categories have found applications, especially, or I would say only in homotopy theory, actually. So it's been applied in equivariant homotopy theory, where you do not work internal to spaces, but instead you work internal to G equivariant spaces, where G is some group. So this is a very powerful point of view in this area. It has applications in condensed mathematics and also in motivic homotopy theory. So I put some references here, and you can, if you download the slides from the webpage, you can go to the articles and sort of try to recognize some of these internal categories that are being used there. All right, so now we come to the goal of this talk. So we have seen these two flavors, namely the enriched and internal infinity categories. And I want to say there are definitely more, but the point is that most concepts of category theory should have suitable adaptations for these flavors. So for instance, you would have, in these two examples, you would have a notion of enriched and internal colimits, and also variants of Kahn extensions, colimit completions, and even fibrations. So maybe fibrations are not as important if you work enriched, but definitely they play an important role if you work internally. So these are all different aspects of category theory that should have some counterparts in these different variants. Right, so the goal of this talk is to produce these specialized category theories in a uniform way for all these flavors of infinity categories. And we will use double infinity categories to do this. And well, I'm certainly indebted to many category theorists. So I would like to mention Street and Walters, Wood, Verity, Schumann, and also the work of Emily Riehl and Dominic Verity on infinity cosmoses has been very inspiring for this project. And yeah, like I said in the introduction, so we are really gonna give an infinity categorical version of pro-arrow equipment to deal with this problem. All right, so the plan is first, I want to say something about double infinity categories, maybe sort of, I want to stay sort of informally. I don't want to be very precise during this talk, just give you an idea of what these objects are. And then we're gonna see the definition of infinity equipments, and I will say something about formal category theory internal to an infinity equipment. All right, so let's start with some motivation for double categories. So maybe you have not seen the definition of pro-arrow equipments, and I keep saying this word, so I want to sort of motivate this a bit. So essentially, we want some ambient playing field in which to develop category theory, by which I mean you have all these different variants of category theories, and whenever you have a variant, you want to put it in an ambient categorical structure and then develop the category theory internal to this ambient categorical structure. So what should this categorical structure be? And I just want to highlight a sort of guiding example. So this guiding example is more like an observation. So it's the observation that most aspects of infinity category theory can be purely phrased in terms of two things, namely functors and profunctors. So the definition of a profunctor goes through in an infinity categorical context like this. So a profunctor f from C to D between infinity categories is just a different name for a functor from D up cross C to spaces. So this is the convention that will be used throughout this talk. Yeah. So one example of a profunctor is one that you can associate to every infinity category, and it's so to say the mapping space profunctor. So it goes from C up cross C to spaces, and it assigns to any pair x, y the space of maps from x to y in C. So this will be my notation of the mapping space. So in strict category theory, this would be a set of maps, but here it's a space. And yeah, so you can get this profunctor by just looking at a Juneda embedding for C and then adjuncting this over to get this profunctor. So yeah, this is an important example of a profunctor. So like I said, most aspects can be sort of phrased in terms of these functors and profunctors. So let's give an example of this. So if you take C to be an infinity category and F to be some functor from I to C, where I is again an infinity category, then you can look at less conextensions of F. So let's say G from J to C is a less conextension of F along a functor W from I to J. And well, let's say G is just a functor for now, and then it's the less common extension if and only if when you look at the following profunctor, which has a horrible description, I guess. I mean, it takes some seconds to parse. So this profunctor is defined using this end here. And yeah, so if this profunctor is sort of equivalent to the following profunctor, you have the profunctor, the mapping space profunctor on C, and you restrict it in one variable along G, and then these two things should be equivalent as profunctors, by which I mean there should exist like an invertible natural transformation between these two profunctors. And if this is the case, then G is the less extension of F. But what this really wants to say is that sort of C is the profunctor that is sort of co-represented by the functor G from J to C. So that's another way to phrase this. So sort of the takeaway from this guiding example is that the candidate ambient categorical structure in which we could develop a category theory should have like two directions for arrows. It should have a functor and a profunctor direction. And it should also have some way in which functors may represent profunctors. Like in this example, you would say that C is the profunctor that's co-represented by the functor G. Right. So this is sort of the motivation, and now we want to make this more precise. So so this naturally brings us to double infinity categories, and let me give a imprecise description of what a double infinity category is. So in some way, it's like a double category, but now you replace every occurrence of sets by spaces. So in particular, you have a space of objects, a space of vertical arrows, a space of horizontal arrows, and a space of two cells, which you again can picture as these squares. But now there's something a little trickier to this. So if you want to compose to two cells, for instance, then there doesn't exist a unique composite up the nose, but still on the nose, but just a unique composite up to contractible choice. So for instance, if you want to compose these two cells, then there exists a space containing all the possible composites of these two cells, and this space is contractible, by which I mean it's like homotopy equivalent to the points. So that's sort of the vague idea of what a double infinity category is. So just want to give a slightly more precise definition. So maybe you've seen a definition of double categories as being a sort of a category objects in categories. And you can run the same definition in infinity categories as well. So a double infinity category would be a categorical object in the infinity category of infinity categories, which is to say that it is a simplicial object displayed like this. So delta is my notation for the simplex category. Yeah, so this functor P comes with an extra condition, the so-called Siegel condition should hold. So let's say n is some natural number, then you have these inclusions in delta from 1 to n, which sort of selects two consecutive vertices. And this should give you an equivalence like this. So you project along these inclusions from 1 to n, and you get like a functor like this. And you see this fibered product also has some p zeros that appear, and that sort of come from the fact that these inclusions from 1 to n, they sort of overlap at some vertices. Right. So I see there's a question. So what is the notion of equivalence of double categories that is induced by this definition? So yeah, I would say it's just, I mean, this way it would be a level-wise equivalence. So if you have a functor from P to Q, where P and Q are double infinity categories, then it's equivalence if and only if it is an equivalence on Q0 and or on level 0 and on level 1. I mean, there are also different ways to really describe such an equivalence, but this would be like the most basic thing that you could say. Yeah. Right, so some notation, or convention, I would say. So the objects and arrows of P0 will be called the objects and vertical arrows of P. So that's to say that P0 is the vertical category of P. I think this is just maybe opposite to the convention that Nima used, but I mean, we use this, and then the objects and arrows of P1 are called the horizontal arrows and the two cells of P. So that will be the terminology in place. So let's see some examples. So if C is an infinity category with pullbacks, then you can construct following double infinity category that would be maybe familiar to you, or at least double category. So you can construct this double infinity category of spans in C, where the objects are given by the objects of C, the vertical arrows are given by arrows of C, and the horizontal arrows are now given by spans. And composing horizontal arrows is just by the usual composition formula for spans, so just by constructing pullbacks. And this example has been constructed by Rune Haugsheim. So this is one basic example of a double infinity category. More advanced would be the following. So you can construct the double infinity category of infinity categories, which is sort of, this construction is implicit in the work of Ayala and Francis, but you can see some recollection of this construction in one of my papers. So how can you describe this double infinity category? Well, it has objects given by infinity categories, vertical arrows given by functors, and horizontal arrows given by profunctors. So throughout this talk, the horizontal direction will always be the profunctor direction. So yeah, maybe you can imagine that defining a double infinity category would be quite complicated to say. I mean, maybe for double categories it's slightly easier, but for double infinity categories, you really have to define a simplicial object in cat infinity and then show that a single condition holds. So this is usually quite complicated, but one trick that really is useful when you want to construct this is by viewing pro-functors as certain correspondences. So maybe you know this from categories, but it's also true for infinity categories that you can describe a pro-functor as sort of a correspondence. So a correspondence is just a functor from E to 1. So this point of view is very convenient if you want to really write down this double infinity category in practice. Right, so this example that I gave can be generalized. So for a suitable infinity category E, for instance, you can take E to be an infinity tuples or any bicomplete locally Cartesian closed infinity category will do here. You can define a double infinity category of infinity categories, functors and pro-functors, which are now internal to E. And likewise, for suitably monoidal V, you can construct a double infinity category of infinity categories and functors and pro-functors, which are now enriched in V. So this example of like this enriched pro-functor example, this has been constructed by Runa Hauseng. Right. Okay, now I want to say something about infinity equipments. Okay, so maybe if you know the story for pro-arrow equipments, you know that companions and conjoints play a central role, and this will again be true. If you don't know anything about pro-arrow equipments, then I want to just say something that take P to be a double infinity category, then we have these two directions, which were already good from our guiding example. Like we said that we want to have two directions. We also wanted a way that functors may co-represent pro-functors, and this sort of idea is sort of encoded using companions and conjoints. So it's like the sentence says, we will need a way in which vertical arrows in our double infinity category may co-represent horizontal arrows in P. So this goes via the notion of companions and conjoints, which can be viewed as like companionships and conjunctions can be viewed as sort of double categorical analogs of adjunctions. So there's a question. So on which level should we consider this enrichment if we would restrict to double categories? On the level of morphisms or rather on the level of squares of double morphisms? So I think this is about this example by Runa. Right. Okay, so so this is just an ordinary double infinity category. So it's a simplicial object in cat infinity. So for instance, this thing in level 0, this would be an infinity category because it's a simplicial object in cat infinity. And in level 0, it would be the infinity category of V enriched infinity categories and enriched functors between them. So like the simplicial object is not a simplicial object in enriched infinity categories, but really a simplicial object just in infinity categories. So maybe that's that answers your question. And otherwise, maybe we can leave it. Okay. Yes. All right. So let me continue with the story about companions and conjoints. Okay. So let me give the definition of a companion. So this is completely similar to the case for double categories. So you start with some vertical arrow in your double infinity category P. And then a horizontal arrow F from X to Y in P is called the companion of F if there exist two cells, namely the companionship unit eta and a companionship co-unit, epsilon, which are of this form, as described on the slides. And they should satisfy some triangle identities, which really the following two identities. So you can sort of vertically compose this unit and co-unit, and you would need to get the vertical identity on the vertical arrow F. And then likewise, you can compose the unit and co-unit horizontally, and you would need to obtain the horizontal identity on F. So this is like at first sight, this must seem, yeah, this looks completely the same as for double categories, but there's like some subtlety that's hidden here. So here between these composites, I wrote this equivalence sign, which really means that so part of the problem of giving a companion is really that you should exhibit some homotopy that connects the left composite with the right composite, or the right two cell. So this is really a subtlety that's sort of hidden here. All right, so you can also run the same dual definition of conjunctions. So we take F to be a vertical arrow in P, then a horizontal arrow F prime from Y to X is called the conjoint of F when there exists two cells which look very similar, but there's been some rotations. So we have eta prime, which is now called the conjunction unit, and epsilon prime, which is called the conjunction co-unit. And again, you can compose these two cells vertically and horizontally. So if you compose them vertically, you would need to recover the identity on the vertical arrow F, and then you can compose them horizontally, and you will need to recover the horizontal identity on F prime. So this is more or less the definition, and yeah, just gonna use this. And now before we come to the definition of infinity equipments, I just want to say the following. So maybe if you're familiar with pro-arrow equipments, what I'm going to say now might be very familiar to you. So if you have a double infinity category P, then you have the following equivalent statements. So you can ask for P to have all companions and conjoints for vertical arrows. But you can also ask for the source target functor from P1 to P0 cross P0 to be a Cartesian fibration. And likewise, you can ask the source target functor to be a co-Cartesian fibration. So Cartesian means really like a quotientic fibration. That's just the terminology used here. So these things turn out to be equivalent, and to prove this, you essentially prove it in the same way that you have done for pro-arrow equipments. So if you, for instance, in 2, if you assume that 1 holds, you can construct all these Cartesian lifts just by composing with companionship and conjunction co-units or units. So that's a way to go from 1 to 2. But essentially the same proof applied. Just to be more precise in some way. But like there are some infinity categorical subtleties here, but you can work around that, and then you can define what an infinity equipment is, and it's precisely a double infinity category P, so that the equivalent conditions of above are met. So that's the definition. So let me introduce some notation. So if F is a vertical arrow in an infinity equipment P, we will write F lower star for its companion and F upper star for its conjoints. So the conjoint always reverses the direction. That now goes from I to X. Right. Let me see how I do on time. Perfect. Yes, some examples. So essentially everything that you see, every double infinity category that we've encountered is an infinity equipment. So the double infinity category of infinity categories is an infinity equipment. And you can describe the companions and conjoints as follows. So if f from C to D is a functor, then the companion of f is given by this pro-functor. So it's sort of a restriction of the mapping space pro-functor for D. So you restrict it along one of these variables along f. And then you can also similarly show that the conjoint is given by the following pro-functor in this context. And then this double infinity category of internal infinity categories is also an infinity equipment. Yeah. And also something that's not in this on the slide, for instance, this double infinity category of spans. You can also show that that is an infinity equipment. So, all right. So now that we have the definition of infinity equipments in place, we can move to double category theory, or say formal category theory inside an infinity equipment. Let me just give a quick overview of what you can do inside an infinity equipment. So you can essentially phrase the following concepts of category theory. So you can phrase what a fully faithful arrow should be in an infinity equipment. You can give some definition of weighted colimits. You can give a definition of pointwise conextensions, XX squares, can even develop some notion of two-sided discrete vibrations purely using the ambient infinity equipment. And there are definitely more things that can be phrased and developed. But these are just the things that are in the literature now. So I just want to highlight a few of these aspects. I will say something about how to define weighted colimits internal to an equipment, and then I will say something about how to do vibrations inside an equipment. So to define weighted colimits, you need a first technicality of sort of constructing a pro-arrow of cones. So this definition may be a bit technical, but it goes as follows. So if you take W to be a horizontal arrow in an infinity equipment P, where you now should really think about W as being sort of the weight, then you can make the following definition. So if you have F, a vertical arrow of P, then you can define what the pro-arrow of W weighted cones under F should be. So this pro-arrow of W weighted cones, we will denote that by C, and it goes from X to J. So to define this, you require the following. So you ask for every horizontal arrow F from X to J, that if you look at the following space of two cells, where you now compose with W in the target, and these two cells should go to F upper star, which is the conjoint of F. Then you require that the space of two cells is equivalent to the space of two cells from like horizontal two cells from F to C. So this is the definition, and maybe it's a bit hard to parse, and definitely take some seconds to get used to. And well, this equivalent should be natural in F. You know, these all right, okay, maybe this definition is also not super precise, but this is just essentially what it means. So maybe you're more familiar with the following terminology, which sort of also appears in the work of Real and Verity. This pro-arrow of W weighted cone C is also known as a right lifting of F upper star through W. This is the definition. All right, so now to define weighted colimits, essentially do the following. So let's say you're in the same context as before. So so again, you have this weight W and you have this arrow F. Then a vertical arrow G from J to X is called the W-weighted colimit of F, precisely if the conjoint of G is the pro-arrow of W cones under F. So this is the definition of weighted colimits. And if you, for instance, read Brieux and Verity's work on infinity cosmoses, you will also see this definition there in the context of, I think, virtual equivalence. But this is the definition here. And now, using this notion of weighted colimits, you can define what Conn extensions are internal to an equipment. So these are just colimits rated by conjoints. And some facts is that this abstract definition of what a left Conn extension should be recovers the known concept of left Conn extensions for infinity categories if you plug in P to be this double infinity category of infinity categories. So that's all very reassuring, I would say. Then some other fact is that this also recovers the concept of left Conn extensions for internal infinity categories. That is due to Martini and Wolff, or P, where P is now the double infinity category of internal infinity categories. So yeah, this is sort of a sanity check that this is sort of the correct definition. So something that you can do now, you have the definition of Conn extensions. So one thing that you can make sense of is of a closed monoidal infinity equipment. And I will not precisely say what this means, but if you have such a closed monoidal infinity equipment, you in particular have some internal hum. And yeah, you can suppose that you're in the following situation. So let's say you have an object X and P and some vertical arrow W from I to J. Then you can look at this restriction arrow and then study the famous question whether this restriction arrow has a left adjoint. So usually for ordinary category theory, you would study such a left adjoint in terms of left Conn extensions. And the same you can do now internal to any equipment. So you have the following proposition. So if W upper star has a left adjoint W shriek, then you can look at generalize. So this W shriek would go from the internal hum I comma X to J comma X. And you can ask what this W shriek does on sort of generalized elements. So whenever you have an arrow P from I to this internal hum, then you can look at this composite where you compose this P with the left adjoint of W upper star. And this is precisely the arrow that is left adjunct to the left Conn extension of I tensor I to X along this induced arrow I tensor W. So this I tensor I to X, this is sort of the arrow that is adjunct to P. Now you have this arrow P from I to internal hum, and you can adjunct this I over, and then you get this arrow I tensor I to X. And then the statement is, if you can extend this along I tensor W, you precisely get this image of P under the left adjoint W shriek. There's also some converse thing that you can do, and it's sort of under reasonable conditions, you can really deduce the existence of a left adjoint W shriek if enough left Conn extensions exist. This is perhaps very familiar from category theory. But the same holds true for any, I mean, you can do the same tricks inside any infinity equipment, which comes with this monoidal structure. All right, so this is what I want to say about weighted colimits and Conn extensions. Then try to be quick and say a few words about vibrations and just give you some idea of how you can make sense of this. And so again, we start with P, an infinity equipment, and then you can develop a whole theory of vibrations using some infinity categorical analog of Grandi's and Paret's tabulations, or they also call them tabulators. So maybe you're familiar with this thing, but tabulations are essentially some form of double categorical limits. And yeah, you have this definition or this convention that if P has all tabulations, you also call it tabular. So that's some terminology that I like to use from now on. So if P is tabular, then you can show that there exists a Lex functor, which is called a span representation. And this is something that's also shown that's been shown for double categories as well. I think Susan Neufeld has written something about this, and also, if I remember correctly, Grandes and Perret also wrote something about this. But this also is true double infinity categorically, that you can write down such a Lex functor. So I didn't really say what a Lex functor is, but it's sort of a functor where now the sort of there's some yeah. So I mean the horizontal composition is not like preserved on the nodes. Like there's some Lex cells interpolating between compositions of horizontal arrows and their images. Right. So this is something that you can prove, and then whenever you're in the situation that you have a tabular equipment with a span representation, you can define what a two-sided discrete vibration is. So a span, so you now look at spans in the vertical category of P, and you call it a two-sided discrete vibration if and only if there exists a horizontal arrow f from x to y in P, so that rho of f is given by this two-sided discrete, by the span. So really what this definition says is that the two-sided discrete vibrations are precisely the horizontal arrows that are in the image of rho. So maybe this is a very unorthodox definition of two-sided discrete vibrations, and maybe you've seen a definition of two-sided discrete vibrations internal to a two-category via some representable way. So the something that you can show is that if you start with some two-sided discrete vibration in this vertical category P0, then it's always sort of it's always co-representably a two-sided discrete vibration of infinity categories. So what I want to say with this theorem is that really, whenever you define two-sided discrete vibrations in this way, there are in particular going to be two-sided discrete vibrations internal to vert of P. And maybe I should have said what this notation vert of P means. So vert of P here denotes the vertical infinity two category of P. And this notation vert P x comma y denotes the mapping infinity category that is associated to vert P. So yeah, maybe it's worthwhile to translate it back to double categories maybe. So this is something that you can show, and you can characterize the tabular equipment for which P or for which rho is horizontally locally reflective, which I call the vibrational affinity equipments. And what this precisely means is that for a vibrational affinity equipment P, the horizontal arrows of P may equivalently be viewed as two-sided discrete vibrations. So there's no information loss if you go from these horizontal arrows to this perspective of two-sided discrete vibrations. So what this precisely means is that this functor rho x comma y is fully faithful and also has some left adjoints. So it's some sort of a reflective subcategory. So again, I should have said what hor P x comma y means. So this is the infinity category of horizontal arrows from x to y and horizontal two cells between horizontal arrows. And then you have this identification. If you look at the horizontal mapping infinity categories of span P0, then this is given by the slice P0 over x cross y. Now, something that you can spell out is if you start with some Cartesian closed vibrational infinity equipments and look at this internal notion of two-sided discrete vibrations, then this behaves perfectly fine like you would expect it to. So for instance, maybe you're used to computing a co-limit of a diagram by just looking at like some slice category of cones and then identifying an initial object inside the slice. So this is something that you can do also in this setting if you're in the situation of being a Cartesian closed vibrational infinity equipment. So that's very nice. So some example of a vibrational, such a vibrational and Cartesian closed infinity equipment is this infinity equipment of internal categories. All right, so a last thing that I want to say about these vibrations is you can also characterize span double infinity categories using this notion of vibrational infinity equipments. So this is in a very, I guess, precise way, a sort of double infinity categorical analog of a result by Carboni-Kazanjian streets for two categories where, so this result of these three alters is about recognizing span by categories. So for double infinity categories, this result looks as follows. So if you have P, a double infinity category, then you can show that the following assertions are equivalent. So you can ask for P to be equivalent to a double infinity category of spans. Then you can ask for P to be vibrational, and with the property that every span in this vertical category P0 to be a two-sided discrete vibration. And then you can ask for the span representation for P to be an equivalence. And all these things all these assertions are equivalent. So that's something that you can do using this machinery. I just wanted to highlight. So this concludes this talk more or less. I just want to say some things that you can do in the future. So it would be worthwhile to so now we've seen this theory of infinity equipment. You might wonder, how does this relate to the infinity cosmoses of Emily Real and Dominic Verity? And well, there should be some precise relation between those two. So if you go to the work, if you read the work about infinity cosmoses, you see that every infinity cosmos has an associated virtual equipment. And this should be sort of evidence for the fact that every infinity cosmos has an underlying infinity equipment. So that would be something that would be nice to make precise, but I just want to warn you that this might be very complicated to do. So something that's also nice to do would be like co-limit co-completions internal to an infinity equipment, which is something that I'm working on right now. And then maybe you're familiar with Lurie's higher algebra and you see some definition of operatic conextensions in there. And I want to show that this sort of also can be like these operatic conextensions are really conextensions internal to some infinity equipment, which might somehow make this whole idea of operatic conextensions, which is notoriously difficult, more clear, I think. So it would be nice to sort of treat enriched infinity category via infinity equipments. So there's also already some existing work of Vladimir Hinich on weighted co-limits in this context. And recently, Adrian Heine has developed some extensive theory of enriched infinity categories. But what I want to say is that, like enriched infinity categories, we had all these models for these objects, and these models are quite complicated. So especially developing an enriched infinity category theory would be quite complicated. But sort of using this infinity equipment, you can sort of move all the complicated stuff in just the definition of the infinity equipment of enriched infinity categories, and from there on it's just smooth sailing, because then you can just interpret the category theory internal to this infinity equipment and get a theory of enriched infinity categories. All right, and then something that's more out of my comfort zone would be something about the type theory for infinity equipments, and this would be, I guess, super complicated to do. And well, I really should say I'm not a type theorist, but So some work in this direction was recently done by Neil and Licata, and yeah, perhaps that might be relevant. But I mean, it would be nice to have something like this, but this would be well, I don't know. I don't know how this goes. So yeah, so with that, I want to conclude my talk. So if you want to see the references, I think the slides will be up on the webpage. Well, thank you so much for your attention.
Thank you so much. Sorry, thank you. Okay, we have some time now for questions. And there's already a question from Nathaniel. So Nathaniel, please. Oh,
Hey, thanks for the talk.
oh,
It looks like many of your results have analogs in the one-dimensional setting. So the two settings seem to behave quite similarly. I was wondering, are there any results from the one-dimensional setting that don't carry across the infinity setting, or are there any aspects which behave particularly differently, or do they actually parallel each other very closely?
Yeah, thanks for the question. Yeah, so until now, I haven't come across anything from like from ordinary program equipments that doesn't translate to the infinity categorical setting. And I would say like I have the firm belief that everything is sort of parallel. But yeah, I mean there are some subtleties in this enriched. I mean in the infinity categorical setting where you really have to deal with homotopies and everything. It's like sort of yeah. I mean yeah, it's sort of more subtle, but I would say everything parallels quite nicely.
okay, thanks. And then Callum, you have your hand up.
Hi, Jaco. Great talk. Thanks for it. You were talking, or you defined these infinity profunctors as, infinity functors into spaces. I was wondering if there's some kind of infinity categorical Grothendieck construction which instead describes them equivalently as some kind of, discrete off vibration or something like this.
Yeah, so you can view these profunctors as two-sided discrete vibrations, and especially you can, if we go back a few slides, then something that is true that is like the infinity equipment of infinity categories is vibrational. So you have the span representation, and the span representation in the case that P is cat infinity. So the target would be or the domain would be profunctors, and the target would be spans. But the essential image of this functor really selects the two-sided discrete vibration. So the span representation is really some form of a Grothendieck construction, I would say.
Cool. This reminds me of Mark Webber's elementary two topos theory kind of ideas in that. This kind of fully faithful span representation of an arrow.
Yeah. It might be something that's very.
Yeah. All right. Thanks.
Yes. All right.
I actually have two questions. One is it true like in the one version that the enriched categories are not tabular?
So I believe they are tabular, but they are not vibrational. So you would have a span representation, but in the enriched setting, you can't view. I think you can view enriched profunctors as these two-sided discrete vibrations. So there's some information loss when you pass to two-sided discrete vibrations in enriched setting. But I do believe they are tabular.
Oh yeah, I guess that's not the part that fails. And the other one is, are there any phenomena like similar to where you have to replace pairs with simplicial and cosimplicial objects in infinity category theory that happen here?
Sorry, can you repeat? Could you
Well,
repeat the question?
There are some like very famous kinds of limits and co-limits in one category theory where you have to where they have pairs, but you in an infinity category theory you have to replace them with simplicial or co-simplicial objects.
Yeah.
Are there
Yeah, so-
any similar things that happen here?
Yeah, so for instance, in a definition of like the equipment of internal categories, so first I want to say like internal categories are defined as sort of simplicial objects. And then sort of if you want to make sense of the composition of internal profunctors, you really do some sort of, you really have some bar construction formula. And this is really a co-limit that's indexed over delta up. So yeah, I think usually all sort of co-equalizers are replaced by co-limits over delta up in the setting. Yeah, so that's definitely something that you see often in this business.
And then there's one question in the chat for you, Jaco, from Lynn Moser. I'll just read it out. It says, thanks for the great talk. Is the minimal data of a companion pair that you gave equivalent to having the full data of a double infinity functor from square 1 into P?
Yeah, thanks for the question. Yes, this is something that is true, and it's so I have this project with Fernando Abian, Martina Rovelli, and Victoria Ozanova, where we work on the squares functor, and this is also something that we show. So I think this project is not entirely finished, but at least this thing we would have. So it's sort of the thing that's sort of parallel to having a homotopy adjunction and really a coherent functor out of the free adjunction. And there's really a parallel to this story for double categories, like Lynn said, that if you give like this definition of a companion, then you can really upgrade this datum of a companion to a honest functor out of squares of 1 to P. So this is something that you can show. Yeah.
Okay, thank you. Okay, I think for the sake of time, so we can start the next talk on time. We can thank Jaco again for the talk. Thank you very much.